Okay, video lecture series part 1, star life cycles, the first 2 stages, and red dwarfs. So, we divide stars into 3 groups. Those 3 groups are based on size, and they're called red dwarfs, low mass stars, and high mass stars. So the sizes associated with these 3 groups are red dwarfs are the smallest kind. They're less than 0.4 solar masses. Now remember, this symbol right here, the circle dot, stands for sun. So M circle dot means the mass of the sun. So when I say red dwarfs are less than 0.4 solar masses, that means that the red dwarfs are about 40% the size of our sun and smaller. Now, low mass stars are the medium category. They're between 0.4 solar masses and 4 solar masses. So between smaller than our sun and about 4 times the size of our sun. That means that our sun is a low mass star because it is 1 solar mass. And then the final category of stars are high mass stars, which are greater than 4 solar masses. Now, the reason that we divide stars up into these 4 categories is that each one of these, red dwarfs, low mass stars, and high mass stars, has a different life cycle. They all start with the first same 2 stages, though. So that's why I'm using this time to tell you about the first 2 stages for all of them. And then I'm going to do the life cycle of the red dwarfs individually. Now, one word of warning. These names are a little bit confusing because if I asked you which one of these would be the lowest mass, you might say low mass stars. But remember, low mass is actually the medium category. You might want to call these small for red dwarfs, medium for low mass stars, and large for high mass stars. Okay, so now the very first stage of any star's life is called the Protostar Stage. The Protostar Stage. This is what we call the formation phase of a star's life. It's all called the Protostar Stage. Now remember, we talked about how our sun formed, and all stars form that exact same way. We all formed out of nebulae. Here we go. Give me a second. So every star forms out of a cloud of gas. If you want to look at this figure at home, it's figure 13.3. All right, so this is a cloud of gas called a nebula. Now, not every nebula can form a star because we need this cloud of gas to collapse if it's ever going to become a star. So we need a cloud of gas that will be easy to collapse. Now, what are the options here? Well, first of all, let's think of temperature. Let's think of temperature. Would high temperatures or low temperatures be easier to collapse? Well, if you remember, high temperatures mean the gas is moving really fast. That means it's harder to pull it together because it wants to spread out. So low temperatures are best for a cloud to form a star. Now, we also should think of density. High densities mean there is a lot of material in a small amount of area. That's going to mean there's a lot more gravity per area as well. The more gravity you have, the easier it is to collapse this cloud. Now, what that means is that it's going to be easier to collapse a cold, dense cloud. That cloud is going to collapse, and as it collapses, it's going to get hotter and hotter and hotter. Now, the very center of the cloud will be the hottest and densest place, so it will start to glow. We call that central part of the cloud the protostar. Now, another thing that will happen to that cloud as it collapses is it will start to rotate faster and faster and faster. For a review of this material, look over the file that I posted on Canvas about how our solar system formed. Now, as it rotates faster and faster, the cloud of gas tends to flatten out like a pizza. The only part that doesn't flatten out is the protostar itself because its heat resists the collapse. Its heat and light resist the collapse. The rest of the cloud will become planets if there's enough material. The protostar, however, will continue to shrink and get hotter and shrink and get hotter and denser until the very center starts to undergo hydrogen fusion. Once hydrogen fusion starts, the protostar stage is over. Now, one thing to note is that not every star is going to go through this process at the same rate. You would imagine that bigger stars might take more time, but it's actually the reverse. The bigger a star is, the more gravity it has, and therefore the faster it collapses. Now, not every protostar successfully becomes a star. Some of them fail. If the material in the cloud of gas is too large, if it has more than 200 solar masses, it actually causes so much fusion that it breaks the cloud apart and you get nothing. On the other end of the scale, if you have too little amount of mass, for example, if you have less than about 0.08 solar masses, as seen here, then you don't actually produce enough pressure and temperature as you collapse because of your low gravity in order to get fusion started at all. Then you become what is known as a brown dwarf. A brown dwarf is a small, cold ball of hydrogen and helium that never started fusion. In this picture right here, every one of those circles actually is a failed star, a brown dwarf. A brown dwarf would actually look a lot like a Jovian planet, because a Jovian planet is also basically a ball of hydrogen and helium. The only difference is a brown dwarf would be 100% gas. This is a picture. This is not a real photograph. This is something that an artist drew of approximately what a brown dwarf would look like, but you can see it looks a lot like Jupiter. All right. Now, the second stage of every star's life begins as soon as the hydrogen starts fusing in the protostar. As soon as hydrogen fusion starts, the star is called a main sequence star. So after the protostar stage, you have the main sequence. The main sequence is specifically defined as the time when a star is burning its hydrogen in its core, when a star is fusing hydrogen in its core. Now, we don't need to talk too much about the main sequence because we already talked about one main sequence star, and that's the sun. Now, as you remember, the sun has all of its hydrogen fusion going on in the core. So right here in the middle of the star is where the fusion happens. Around that, you have a radiative zone where the light is slowly working its way out of the star, and then a convection zone on top of that where gas is churning up and down towards the center and then away from the center. We don't need to talk too much about the main sequence because everything we said about the sun applies to all main sequence stars. Now, if the main sequence starts when hydrogen fusion starts in the core, it's going to end when hydrogen fusion ends in the core. So remember, the whole star is made of tons of hydrogen. It's about 75% hydrogen, about 25% helium on average. So it's a little bit weird that the star will start to die as soon as just this part runs out of hydrogen. Even if there's hydrogen out here, and there will be, the star will die when this runs out of hydrogen. Well, why can't this hydrogen go into the core? Well, this hydrogen, remember, when it fuses, turns into helium. So this whole region, the only place it's hot enough to fuse, will become full of waste. It will become full of helium. And there's no way for the hydrogen out here to come into the core if the core is full. If you could scoop it out with your convection zones, if you could scoop them out with the convection zones, you would be able to do it. But unfortunately, in most stars, the convection zone is not scooping where the dead region of the star is going to be. Now, those are the first two stages of every star. But now I'm going to tell you what happens to red dwarf stars after these two stages. So these first two stages are the same no matter what life cycle we're doing, but now we're going to do the red dwarf life cycle. So if we were going to do the red dwarf life cycle, the first two stages, again, would be protostar and then main sequence. Now, after the main sequence, red dwarfs will die in a different way than any other star. And the reason for it is because the internal structure of a red dwarf is a little bit different than our sun. So let's say we looked at a little bit smaller of a star than our sun. If we did, you'd see all the same layers, but the layer that shrinks the most as you go to smaller and smaller stars is the radiative zone. So see the core shrunk a little bit, the radiative zone shrunk a little bit, but the convection zone shrunk a little bit, but the radiative zone shrunk a lot. Now, if we look at an even smaller star, eventually we're going to get to the point where the radiative zone has gone away. So here we've got a core and a convection zone that touches it. Now, the reason that that's important is that this is a red dwarf star. Red dwarf stars do not have a radiative zone. They only have a core and a convective zone, a convection zone, which touches the core. That means that as soon as the hydrogen is used up in the core, the convection zone can scoop up the used up helium and push in the hydrogen from outside of the core. That means that the red dwarf star gets to keep going for much longer. It gets to use up all of its hydrogen and turn it all into helium. Now, that's important because that means that once the main sequence is done, once the hydrogen is used up, all that's left is a big ball of helium. So I'm going to call the third and final stage of a red dwarf's life cycle the helium ball stage, because it's a big ball of helium. Now, if that doesn't sound like a very scientific name, it's because I made it up. Why did I have to make up a name for what red dwarfs turn into? Well, it turns out that none of them have ever died. None of them have ever died. So, if you remember, I mentioned that our sun would run out of fuel eventually in about 6 to 7 billion years. And that's because the rate that we're burning through hydrogen, along with the amount of hydrogen we have in our core, you can calculate the approximate amount of time it's going to take. Now, the bigger a star is, the more gravity it's squeezing its core with. And therefore, the hotter its core is, and therefore, the faster it's going to burn its fuel. On the other side of the spectrum, the smaller a star is, the slower it's going to burn its fuel. So if a star like our sun, a low-mass star in about the middle of the range of the low-mass stars, our sun will last approximately 12 billion years on the main sequence. High-mass stars might last about 25 million years, which is much less time, whereas some red dwarfs can last 200 billion years. Our universe has only been around for 14 billion years, so no red dwarf has ever gotten to the helium ball stage. All right, stay tuned for part 2, low-mass stars.